All right, so here's our practicum problem for tonight. We've got a beam made out of aluminum, and this is for 6061 aluminum. It's got a modulus of elasticity of 10 MSI. It's loaded up with 10 kips, so 10,000 pounds of force. It's 8 feet long, and each problem has a different cross section to that beam. In the first one here, we've got a 4-inch by 4-inch square beam, but it's got a hollow section taken out of it. In the second one, we've got a 4-inch diameter solid rod, solid circle. And then we've got a 4-inch diameter circle with a 2-inch diameter hole taken out of it. And the goal in each problem is to find the elongation, to find out how many inches or fractions of an inch this beam stretches out by when it's loaded in this way. So the critical step here is figuring out the areas. So let's work through the first one, and then we'll come back and do the others. So I'm going to cover up the other two here while we work on the first one. So the first thing to do is figure out the area, because the first step we have to make is take the force and turn it into a stress. And stress is force divided by area. So we need the cross-sectional area. The way to think about dealing with areas that are missing sections is to figure out the area of the whole thing and then subtract out the area of the inside of the piece that's missing. That's how we create a hollow section. So that big section here, this is 4 inches by 4 inches. So it's got an area of 16 square inches. The smallest section is 2 inches by 2 inches. The missing piece in the middle is 2 inches by 2 inches. So that's 4 square inches. We're going to subtract those. So we have overall 12 square inches to work with. That's our area. Now be careful. We could have phrased this a little differently. I could have said, for example, you've got a 4-inch by 4-inch square beam with a 1-inch wall thickness. And then you'd have to figure out, well, okay, if I've got a 4-inch by 4-inch beam and it's got this hollow piece taken out, the walls are 1 inch thick, how much area am I dealing with there? Well, you treat it the same way. You've got 4 inches by 4 inches, you get that 16 square inches for the whole cross section. And then from the 1 inches, if it's 4 inches all the way across, you've got 1 inch there, 1 inch there, so there must be 2 inches there. 2 inch by 2 inch in the middle. But sometimes it's specified in terms of inside and outside dimensions. Other times it's outside dimensions and wall thicknesses. So be careful of that. So here 12 square inches is our area. So our stress, we've got 10 kips spread out over 12 square inches. And if we calculate that out, it's not going to be a pretty number, but we can apply the same principles that we've applied so far with respect to rounding. I'll arbitrarily keep 5 sig figs in the calculation. So we've got 10 kips and 12 square inches. That's going to give me a stress of 0.83333 kips per square inch, or KSI. So that's the first step in our chain here. We've used the area and the force to get the stress. Now that we know the stress, we can figure out the strain. Stress and strain are connected to each other by Hooke's law. Hooke's law says that the strain that we get is the stress divided by the modulus of elasticity. So we know how much stress we've got. That's how much force is on each square inch. The strain will tell us how much each inch grows by. The modulus is 10 MSI, but remember that we've got to make the units match. I've got KSI for my stress, 0.8333 KSI. I've got to put my modulus in KSI also. MSI is million, so KSI would be 1,000. I've got to add an extra 3 zeros here. So I'm going to have 10,000 KSI. That's my modulus. 10 MSI, 10,000 KSI. Now the units cancel out, and I'm going to get an even smaller value for my strain. I'm going to get, and scientific notation can be helpful here. We'll use 8.3333 times 10 to the negative fifth, just to avoid having to write a whole bunch of leading zeros. If we did write it out, and you may have written that out, that would be 4 zeros, an 8, and a bunch of 3s. Now, what that strain represents is the amount of length each inch picks up, or the amount of length each foot picks up, or the amount of length each meter picks up. It's telling you the ratio between the elongated length and the regular length, the unloaded length. Well, this isn't very much. In fact, if this is inches, this is 83 millionths of an inch. Not a very large amount at all. That's because the stress here is relatively low. We're spreading out 10,000 pounds over a lot of square inches. So the material's fairly strong, and we've got a low stress. So we shouldn't expect a lot of strain. Now, to figure out the elongation is the strain times the length. So that's right there. Elongation is the strain times length. The strain tells us how much each unit of length grows. The length tells us how many units of length we've got. So here we've got 0.0008, oops, last one, 0.0000833333. That's inches per inch or foot per foot. It'll take on whatever units of length you plug in. So I'm going to go on the 8 feet. If I multiply those two together, I get 0.00066667 feet. Or if I wanted to convert that into inches, which would be a little bit clearer, I get 0.008 inches. So 8/1000ths of an inch. So this 8-foot long beam loaded up with 10,000 pounds of force stretches out overall by 8/1000ths of an inch.
So as far as significant digits on this,
Yep.
like I have 7.9968 times 10 to the negative third inches.
Okay. You might have had some round off someplace because I kept everything in my calculator and it came out exact 0.008.
Oh.
Because the 12 over here canceled with the 12 that I multiplied this by. And it's the 12 that causes everything to be rounded. I'd go back and check your numbers, make sure you're not rounding off wrong someplace.
Okay. But in general, do you try to round to the nearest thousand?
No, I mean, it's the same rules we've had before. You'd want to have a typical good number of sig figs to have would be 3 in the end of the problem, which is why I kept 5 throughout the range. Now remember, when you count up sig figs, the leading zeros don't count.
Correct.
So I suppose if I really wanted this to be 5 sig figs, I'd have to write it out 0.0080000 for 5 sig figs. But because this came out exact when I multiplied it on my calculator, I dropped those extra zeros. But if you were to round this off, 3 sig figs wouldn't be bad. You know, then you're down to 0.0008 or 0.00800. But if I left it as this one here and I rounded it to 3 sig figs in terms of feet, it would be 0.000667 feet.
Okay.
To 3 sig figs in the end. But here I left the door wide open in this problem. I just said find the elongation. So you could have left it as feet. It's just a little bit clear, at least for me, because I deal with machining and such. 8/1000ths of an inch is a heck of a lot easier for me to visualize than 0.0006667 feet.
Copy.
I don't typically work in millionths of a foot. The thousandths of an inch I deal with all the time. I mean,
Gotcha.
8 thousandths of an inch, just for physical reference, for those of you who might not be so familiar with it, 8 thousandths of an inch is about the thickness of 4 human hairs put together. It's about 4 sheets of paper put together. So 4 thin sheets of paper. So it's not very much. That means this beam is relatively stiff. It's got low enough stress that it's not really going to change shape all that much. Any questions on that process? All right, let's try another one here. Let's do the circular. Now, even though the dimensions are similar, here we've got a 4-inch diameter. Not quite as big of an area as 4 inches by 4 inches. 4-inch diameter is going to be smaller in area. So we'd expect a little bit higher stress here if we were dealing with that full 16 square inches here. We'll see if we hit 12 square inches or something bigger or smaller when we take that into account. The area of a circle is pi times the radius squared. So you got to watch out for your radii and your diameters. Here I've got a 4-inch diameter, so I've got a 2-inch radius. So this will be pi times 2 inches squared. And if I go to my calculator on that, 2 inches squared is 4 square inches times pi. And to 5 sig figs, I get 566 square inches. So slightly larger cross-sectional area than our hollow beam. Our hollow beam had 12 square inches. Here we've got a little bit more area, but just a little bit. But that'll mean slightly less stress, which will mean slightly less elongation. The numbers are uglier, but we're going to have slightly less stress here. So slightly less strain and slightly less elongation. So we'll get something a little less than 8 thousandths of an inch. So let's see how it works out here. First, we'll find our stress. Stress is force divided by area. We've got that same 10 kips of force, but now we're spreading it out over 12.566 square inches. So we've got 10 kips and 12.566 square inches. That gives us 0.795, looks like 80. And that's kips per square inch, it's KSI. So a little less stress than we had before. We had 0.83333 KSI in the first one. So a little less stress. To find the strain, we take the stress and we divide it by the modulus of elasticity. So we've got our stress 0.79580 KSI. Remember, we've got to make the units match, so we can't just plug in 10 MSI. It's got to be 10,000 KSI, so those will cancel out. And there we get, written out in full format, 4 zeros and 79580. And that's inches per inch or feet per feet. It's the elongation. So each unit of length grows by this very small ratio. Looks like 79.5 millionths is what it grows by. The elongation is the strain, how much each unit of length grows, what factor each unit of length grows by, times how many units of length you've got. So we've got 0.000079580 times 8 feet. And that gives us 0.0006364 feet. Whatever units you multiply by here with your length, that'll be the units on your elongation too. And again, I like to look at it in inches. So I'm going to multiply that by 12, and that gives me 0.0076397 inches. Not a requirement. You could have just left it in feet. That's the problem, leaves it wide open. But for comparison with the previous one we had 0.008 of an inch of elongation. Here we have slightly less elongation because this is actually a little less stressed. Even though we're pulling on it with the same force, we've got more area that we're spreading that force over. So we end up with lower stress and therefore lower elongation. It doesn't stretch out as much. Any questions on that one?
No,
Go ahead.
no, no issues.
Okay, so on the last one, we've got this hollow circle. So there we're taking that 4-inch diameter, and now we're boring out this 2-inch hole. That's going to reduce the amount of area that we've got. So the area is going to be smaller here than what we had in B. That means the stress is going to be higher, which means the elongation is going to be higher. Now, the common mistake that people make when they're dealing with hollow circles, you got something that looks like this. And the classic mistake that people make is if this inner one is 2 inches and this outer one is 4 inches. The first thing people try to do is subtract the two and say 4 inches minus 2 inches. Okay, I've got 2 inches, then go and figure things out from that. They'll either try to do that with the diameter or with the radius. You cannot subtract diameters or radii directly. You got to do the same thing that we did with the hollow square. Find the area of the whole big circle and subtract off the area of that smaller circle. So the bigger circle has a diameter of 4 inches, and we already figured out the area for that from our previous calculation. With a 4-inch diameter, we got 2 inches of radius. So this is 12.566 square inches. The smaller one here, we've got to figure out pi r squared. For the small circle, the radius is 1 inch. So we've got pi times 1 inch squared. So that means we're going to get 3.1416 square inches. So we'd subtract those. So the biggest hurdle in this part of the problem should have been just figuring out the area. So you always take that big area and subtract off the small one. Don't try to mess around with subtracting dimensions. Subtract areas. So you've got 12.566. We're going to subtract off the area of that smaller circle, 3.1416. And we get an area of 9.4244 square inches. So that's a bit of a smaller area than what we've dealt with so far. So we can expect a higher stress, therefore more elongation, more strain, more elongation. So let's figure it out. Our stress is our force of 10 kips, spread out now over this area of 9.4244 square inches. Now that gives me a stress of 1.0611 kips per square inch, or KSI. So our stress finally breaks 1. We've got 1 point something KSI, 1,000 pounds plus a little more, 1,061 pounds on each square inch. So there's our stress. The strain is the stress divided by the modulus of elasticity. So that tells us how to turn our stress into strain, to tell us how much that force for this material turns into a stretch. So we've got 1.0611 KSI. Just like the other two problems, we've got to divide by 10,000 KSI rather than MSI. So when we do that, we've got 0.00001, right? 1, 2, 3, 4. Yep. 1, 2, 3, 4. Get the right decimal in here. Is that right? Yeah, I'm off by one. There we go. So 0.00010611. No units, because that's telling us that each inch is growing by, in this case, 106 millionths of an inch, or each foot is growing by 106 millionths of a foot. It's dimensionless, so it'll take on whatever units we give it. And we can do that in our last part here to find the elongation. We take the strain and multiply it by the length. So we've got our strain of 0.00010611 times our 8-foot length. And that gives us 0.00084886 feet, or multiplying that by 12, which is, again, totally optional. We get 0.010186 inches. So a little bit more than 10 thousandths of an inch. So when the stress is going up a little bit, the elongation goes up a little bit too.
So would it be safe to round it to 0.0102 inches?
Yeah, for 3 sig figs. I don't think anyone's going to break out a laser mic or something that's going to get us down to a millionth of an inch.
Because I rounded in a little bit deeper than you guys did, than you did throughout, but I still came up with the same.
Yeah. Final. I mean, the round off error is relatively benign here, but yeah, if we wanted to round it off to 3 sig figs, we'd have 0.0102 inches, so 10.2 thousandths of an inch. Yep, that'd be pretty typical. So that's not too bad. And in fact, this is pretty much what our homework assignment this week is going to be on, that I'll release on Wednesday. It'll be just kind of calculating out these kinds of stresses, strains, elongations.
You weren't kidding. It's a lot. It's all downhill from here.
Yeah, it's pretty simple compared to
is done.
Trust analysis.
Yeah, once I tried A and I didn't really get it, but right now that you went through all of them, it makes a lot more sense.
Yep, well, that's why we do it. So
I always get it when Tom goes over it.
Yeah.
Yeah.
Hey, Mark, this might be easy, but now you have to remember what we started with and how to figure all that stuff out.
Yeah, that's what I mean. I'm concerned. We get to that final exam, I'm going to be like, oh, we're on easy.
That picture's kind of a good one to have, I suppose. And I'll redraw it again next time, how we get around the loop, essentially, and what our critical equations are. It's not so hard to use them. It's a little bit harder to get a really good physical understanding of what they're telling you. And I'd encourage you to spend that time and effort thinking about what these are really saying and what that really means, versus just being able to plug numbers in and get the right answers out. That's always the challenge. I mean, we can write computer programs to do the calculations. It's understanding what the calculations mean and what they're telling you. That's the harder part.
So you did say for our final exam, we're allowed 1 index card from the first test, 2 from the second, 3 from the third, and then 4 for the exam.
Yep.
So that's a total of, what is that, 9 index cards?
No. Nice. No.
Your math sucks, dude.
Clearly said cumulative.
Yeah, no, it's not cumulative on the index cards, but it's 1 for the first exam, 2 for the second, 3 for the third. You can carry 1 from the other, or 1 from the next, 1 from the previous to the next one, but you'll be allowed 4 index cards for the final.
Okay, fine.
Even though we were doing our final this time, because of the time we lost, we are going to bundle the third exam with the final. So the problems on this stuff, which is relatively straightforward, the problems that we'll do on strength of materials will be counted separately and together with the final exam. So whatever problems I have on there, let's say it's worth 30 points on the final. I'll take whatever you get out of 30 points on those, and that'll become your exam 3 grade.
Oh, nice.
Oh, cool.
So that way we can avoid having to try to work through third exam and then do a final in the first week of May.
Yeah. What day did you say it was? The 27th?
The 29th will be our final.
29th?
So 2 weeks from Wednesday. Anyone have any other questions?
No, I'm good.
No.
No.
All
Good
right.
night, guys.
Have a good night.
Good night.
Take it easy.
Have a great night.
Too.